Hello, my name is Alan Folmsby, and today I'll be talking about physics and physical chemistry, the covalent mock-up. It's an experiment. Quantum mechanics will be demonstrated using strings. It isn't really a string theory, but ropes are like big strings, so I thought I'd use that word. And the major point I want to emphasize today is the non-crossing law, which I'm introducing to standard science. You are directed to use this aspect of reality. It's a mechanistic explanation of how molecules are formed and bonded. And it's a non-crossing of lines between electrons and protons. All right, so I've set up some experiments for today here, and right across the room over here, I'm going to turn the camera around in just a second, and you're going to see the two oxygen atoms forming one oxygen molecule in a mock-up. All right, so I'll just turn the camera around while you're looking at some words here. Okay, so what I'm going to show you is some ropes and weights, and I think I'll just draw a picture of what's going to happen here. I'll get out a piece of paper and draw it for you. All right, I'm walking over. Oh, that's good. I can block my face and talk in the microphone at the same time. So you can see the two ropes over there. And this is going to be representing two oxygen atoms. So at the top we have oxygen, and then near the floor we have an oxygen nucleus. All right, so here's the picture I'm going to draw. Coming up from the bottom are some red ropes. And they have electrons on them at the end of the red ropes. And the other one has the green ropes. And gravity's holding them down. So that's the one I'll be using. So you can see there's this overlap where the top nucleus of oxygen comes down to 2 electrons near the bottom. But the bottom nucleus then has 2 electrons that are beyond the other 2. So there's an intermingling, and the ropes are going to be wrapping around each other for this picture. So I'll just go to the ropes now and show you how this is supposed to go. Alright, so I'm going to back up the camera a bit so you get a wider angle view here. Oh yeah, that's better. So at the top is one nucleus, and on the bottom is another nucleus. For example, here's one little model of a nucleus. We could put this one down at the bottom, and then another one near the top. And here's the second nucleus of oxygen. We'll put that up at the top. So there's the one atom with the red rope hanging down from it, and it has two bonds. So it's a covalent bond. It has two red ropes hanging down. Now gravity is going to be helping us here, and I'm going to now swing it around again in the circle. This is called spin. Alright, so the spin is actually the rotation of the electron around another line between a proton and electron. So you can see it wraps up around. So the electron's not orbiting the proton. The electrons are orbiting a line between a proton and another electron. So the spin can go two different ways for bonding, or the two spins can go the same way for anti-bonding, as shown here. So they're both spinning the same way, so they came close to colliding, like there. See, if they're spinning the same way, they collide easily. But if they're both spinning opposite directions, they mesh instead of clash. That was with the same spin. Now I'll rotate them with the opposite spins, and they won't clash. They will mesh. And then this would be at low temperature. At high temperature, these would be spinning wildly in a higher distance. And they could actually overlap. If the temperature is too high, parallel lines will overlap in one atom. Instead of making a molecule between two atoms, at high temperature, they wrap on each other, just like I showed you there. Two reds got wrapped up with each other at high temperature. Well, let's go to low temperature. You see this is coming around slowly. And they're spinning the opposite ways, so they don't clash. Let me try and make them mesh close together here. There, you see they meshed, they touched, and yet they continued rotating with opposite spins. As opposed to if they had the same spins, they would clash and stop quickly. So I'm going to go back to the text now and explain what you've just seen in more detail. All right, I have quite a bit of text available here. And as you can see in the slide on the bottom, I have 4 protons and 4 electrons in this demonstration. So I have 4 ropes. Each one is connecting a proton to an electron. Now, these ropes do not really represent positions. but velocities. And also they can be combined as fluxes, and a flux squared is energy. Now I think I'll move the camera a bit for a second here. All right, so I've got quite a bit of text over here, and I'm just going to talk about what you saw on the ropes. So this is about the covalent bond in chemistry, in physical chemistry, and this is a mock-up in a live demonstration of the experiment. And I showed you the schematic of the experiment for the mock bond, and the thing that standard science is lacking the non-crossing law. Actually, they've done quite a good bit of work there on quantum mechanics, on all these things using algebra, but now you can translate this into geometry, and that requires the non-crossing law between a line from one proton to electron cannot cross another line between a proton and electron unless a certain event happens, unpairing and pairing. Okay, so this is geometry, and I'm trying to show an analog of molecular facts here. Now, these ropes, of course, are not accurate portrayal of an oxygen molecule in every way, but I contend that it is an accurate geometric analog of some molecular facts. Fact number one: the two nuclei are separated by a distance, just like in this mock-up. Fact number two: one nucleus is in a certain direction away from the other nucleus, and the bond occurs between those two positions, just like in this mock-up. Another thing is the non-crossing law, in which these ropes do not cross each other, just like in a molecule. There's a non-crossing law. Now what I'm using is rope, string, wire, and steel tape measures. Like, for example, I have a steel tape measure over here. So this is actually similar to a molecular bond because it's flat. In my earlier lectures I was telling you about the flat subuniverses, that each electron, that thing at the top is the electron, and my hand is the proton. And they're connected so that in two dimensions the proton controls the position of the electron. That's this dimension, like a knife. It's stiff in that direction of the, you can't push it like you wouldn't want to push on a knife. And the other direction is straight in. The radius is fixed. But there is one free dimension, as you see. The electron is free to move all over in one dimension. So really the interaction between the proton and electron is only two dimensions, and that the steel tape is springy, just like a bond is springy. And this is explained by the the non-crossing law locally. Because, as I explained in earlier things, there's the time is growing out of the proton for gravity, but the mirror image then is a time-like dimension coming into the proton from the electron. That's a counterflow against the space that's growing out of the proton towards the electron. That's why the interaction is local. Even in seemingly empty space, these bonds can interact and have non-crossing events. And they wrap up on each other like the ropes. That's an accurate geometric thing. And the lines exclude other lines unless an event occurs. An event is the unpairing of the electron from a proton and the pairing of the electron to a different proton. And an ohm is the number of events per second. So if you're going to burn up energy and use power, then ohms will be events per second, where you can calculate the power. Now, another thing is that the spin-spin coupling in nuclear magnetic resonance is sometimes quite accurately portrayed here. The spin-spin coupling is those ropes wrapping around each other. Let me point that out a little bit more with the ropes. All right, so we have red ropes and green ropes. The red ropes are coming down from above to an electron at the bottom. The green ropes are coming up from the ground to an electron above. So suppose there's an electron right where my fingers are on the green, and then the red has an electron right where the metal thing is connected to the red, and they're going to interact. These two spins interact. Now, because of gravity, I can only use one of these electrons freely. The other one up there is held onto the ceiling, so that I can't really show you a good experiment today. But the one down here is available for spin-spin coupling. So imagine the green one is spinning around, and the red one is spinning the other way around it. That's the spin-spin coupling of wrapping up, one line wrapping around another line. This is a bond. A covalent bond is when you have two of these, and their spins are opposite, like I showed you before. I'll just spin this a bit. So those had opposite spins. Now I'll show you the same spin direction, and they will clash instead of mesh. So you see, if they spin the same way, the electrons clash, and the non-crossing law prevents them from crossing unless there's an ohmic event in which power is dissipated. So I'm going to move along now back to the PowerPoint. Well, great. I got to show you the experiment. I might do a little more later, but I have a lot of talking to do here, so let me just take a little intermission while we have a message from our sponsor. Hello, it's Alan Folmsby here in my front yard. This is where I discovered the shape of the iron nucleus. Well, great. That was fun. That's my front yard. Okay, so December 27th. I still have a lot of talking to do here. Let me go back to this slide. Now, this is just saying that electron-proton pairs are linked by velocity dimensions, not with distance dimensions, really, in the bond. Michelson and Morley showed that positions are not that important for measuring things in the universe. But a length of a bond velocity is a flux. So there's a velocity of the bond, but it's also how long is the bond. If you multiply a length by the velocity, that is a flux. That is a wave function, psi. Square meters per second is the units of measure of all fluxes. And flux squared is energy, and energy has the same units as torque, foot-pounds. All right, so I showed you the rope experiment there. Red ropes for oxygen atom number 1. I showed green ropes for oxygen atom number 2. And the electrons were at the ends of the ropes, and the protons were at the other ends. Just like real atoms. Now, part of my theory I'm presenting to everybody is that there's a hierarchy of flux. So there's a dimension in the atom, as I've said in earlier lectures, 3 dimensions, and each one is a velocity. There's 2 space-like dimensions and 1 time-like dimension, and each of them is a velocity-like property. Now, the length of that velocity in meters is a flux, and it's called a pair line, the dimension flux. But also in the hierarchy, there's the pair flux, which is 3 pair lines, and that makes up one of those red ropes I showed you. Now, this is revealing the true meaning of the quantum numbers, NLMS. So for atoms and things and orbitals, they have N. And now that the non-crossing law is being used as the truth behind this, how reality really works, now we can show what these quantum numbers mean. The electrons are orbiting not a proton, but a common line. So an electron has a line to a proton. Other pairs have lines. And they're both, the electrons cannot cross that, so they orbit the common line. Angular momentum was explained in these images. So on to the final slide here. I'm going to tell you about the schedule coming up, but hold on a second. I got a little more written material here. Oh, great. I got my camera pointed at the correct thing now. And now you're going to be seeing it. Oh, there it is. It's a computer monitor. But I've got some nice pictures that go along with this. Like, how about the 3 dimensions? I was just mentioning how there's 2 space-like dimensions and 1 time-like dimension. Here they are in the middle. That's the bond between 1 electron on the right and 1 proton and neutron on the left. So this is Blender 3D. I'm going to rotate this around for you here. Oh, that's better. Now I can rotate it. So there's a neutron on the top right and a proton right below it. You see the proton has 3 things protruding from it. This is 3 dimensions of space coming out of the proton. One of them feeds the neutron over here. And 2 of them feed the electron through these large flat things. These are the flat space-like dimensions that I mentioned. And then the 3rd dimension is a time-like flow going the other way. And then the electron is down here quite small. So let's just rotate that again. This is fun. All right, now I have another picture here. Let's see what I... Oh, yeah. Here's the silhouette of oxygen. And so it has all the protons and neutrons treated the same here in red and black. So there's a cube in the center there, and the black protons and neutrons are outside of the cube. All right, so now part of what I'm talking about here is how the spinning actually has something to do with what's going on. When the rope was spinning around there quickly, that's the 23 gigahertz electron spin resonance type of frequency. But the lower frequency is about how many times it unravels completely and reverses direction. That's seen at nuclear magnetic resonance. If you apply, say, 4.7 Tesla to hydrogen, then at 200 megahertz you would get this slow motion. That is how often the nucleus has to provide things to the electrons. It's infrequently. So the spinning of the ropes unravels completely infrequently. But the actual spinning around the rope happens quickly, each cycle. So in the standard science, they used to talk about the magnetic moment of the electron is much larger than the magnetic moment of the proton. But now, that's just a fragmented theory, which I'm replacing with a unified theory. And I told you about the hierarchy of fluxes in here. And you could read this later on, but there's space-like and time-like dimensions. But each space-like dimension really is a velocity. So there's also a wave-particle duality that I've been showing you. The particles, of course, are the electrons. The waves are the ropes. And the ropes have interactions by excluding other ropes or by pulling a proton-electron together or growing apart. So that the exclusion really is what's causing radio. Radio signals are going through a vacuum of these thin films, excluding each other and moving around. So even though the proton in your transmitter is not connected to the electron in your receiver, the electrons in your receiver are getting pushed around by these flat lamina. And so the average velocity of these dimensions is the speed of light divided by 187, and that's E over P, where E is the energy of a proton, 900 million electron volts, and P is the momentum of free space, which I told you about last month, 7 times 10 to the minus 37th cubic meters per second. So the proton is multiplying 3 dimensions of the electromagnetic continuum, and that gives the magnitude of the time-like dimension, TH, because there's a mirror in the proton. Now, the flux is in 3 dimensions. Momentum uses 4 dimensions, so those are different things. All right, now here's the quantum numbers that I told you about, NLMS quantum numbers. N is the number of loops get wound up on a pair line, like 1 or 2 or 3 times that rope went around the other rope. 5 times went around. So that's a high frequency. And then L, quantum number, is how many loops during action remain. It could be 0, 1, or 2. And then M is the reverse and forward torque and action numbers. So you notice the rope winds up in one direction, and then there's torque in the springiness to make it wind up in the opposite direction. And that's why you get these positive and negative numbers here. The spin, I showed you the spin. The ropes are spinning around other ropes. Electrons are not spinning around protons. Electron strings are spinning around other electron strings. And they can mesh or they can clash according to the S quantum number. So I've given you a mechanistic explanation. The wave-particle mock-up was provided where the wave is these ropes. Now, temperature is illustrated. I think I showed you wildly swinging ropes that didn't wrap around to make a molecule with a different atom, but the ropes in the same atom wrapped around each other, preventing molecules from forming. So much like reality. I tend to think this is an accurate model. Now, laminated space is really a B field, a magnetic field, Webers per square meter. A Weber is paralines per second, square meters per second. And I've calculated that 1 Weber is equal to 860 billion pairs per second of flux. And that is like a B field, Tesla's, which is Webers per square meter. But the thing is that the B field is combing the lamina. All those thin two-dimensional things connecting electrons and protons are the lamina. And the B field is the same thing. It's more lamina. So the B field is like a comb going through hair. And it can magnetize iron by doing that. Or by going opposite directions, it can demagnetize iron by combing one way and then combing backwards against the hair. You know how bad that can be. You could be demagnetized. All right, an ampere is flux, coulombs per second. Momentum is not flux. So electrons have momentum when they're spinning around those strings, though. And I'm getting down to my last 2 minutes. We're winding up here for a grand conclusion here. Oh, there it is. That's the end of the page. I better point down at that time there or something, huh? All right, we're almost done here. There it is. The covalent bond was shown with 4 paralines. The mesh or clash spin interactions were shown mechanically. It's not a mystery. Opposite spins are needed for a covalent bond. My name is Alan Folmsby. Today is the 27th of December. The next show will be live Monday at 20 hours, Greenwich Mean Time. Bye. Oh wait, I see somebody sending me messages here. I'm going to delay for a minute. I'm going to read these messages. I'll go to the camera a bit here. All right, I see there's messages. Sorry, last week I failed to check these YouTube messages. I see they're coming. Almost missed you. I'm here now. Bestoic primer. I got some very, very interesting drawings that are related to your tape measure, basically. It's a bread bag twisted in the center of a ring. As the ring is compressed, and you get a helix at 37. Okay, Egyptian. The head mask. Big one, consider properties. Oh, I see. He's sending me messages. Thank you very much. Okay, I'm looking at myself on my monitor now. And you could send me emails if you want to give me a link to something. Thank you very much for this. And I'm going to end the stream now.